Hey everyone, it's me, Billy Younger. I am here to solve a damped harmonic oscillator problem. Specifically, I'm going to solve the generic one where I just use variables like mass m, uh, coefficient of velocity is going to be a quantity negative b, and the spring constant is going to be, of course, k. And we're going to derive the actual solution for that in three different forms. So let me start by sharing my screen. What I've written here is use Newton's second law of motion and Hooke's law to write out the equation of motion for a mass on a massless spring subjected to an air resistance that is proportional to its velocity. Discuss the three possible solutions. So that's the problem we're solving. Let me go ahead and get started by writing solution. So what we're going to need for this particular solution is we need the information about the actual spring system. So I'm going to say the spring constant is K, the mass on the spring, the massless spring, the spring is massless, of course, but the mass on the spring has a mass M. And I am going to say that there is a Hooke's law, which is given by F is equal to negative Kx. And there's also an air resistance, which sometimes is written as a proportional to velocity squared. Sometimes it's just velocity. It's a lot easier to deal with the just velocity than it is to deal with the velocity squared in terms of differential equations. So we're taking that one, and that actually is a very realistic assumption that we're making. Uh, at least in extremely small velocities, on the order of what a mass on a spring would be, and in something that's fairly thin like air. So the air resistance, or force of drag, as I'm writing it here, is actually going to be negative b times velocity, but in terms of velocity, v is x dot. Remember, dot over top of an x means a dx dt, so I could also write this as negative b dx dt. Let's go ahead and write out Newton's second law, which says the summation of the forces is equal to ma. Again, this is the version that we've been using when the acceleration is constant. This acceleration is not going to be constant, so I'm not going to write a as just a vector a. I'm actually going to write it as a second order derivative of x, and I'm also going to make use of the fact that Newton's second law sees this as a restorative force in terms of the drag as well as in terms of Hooke's law. So let's get started. The left-hand side of, oh, the other part I want to mention to you is the summation of forces equals mass times acceleration. We're also dealing with this as just one-dimensional motion, so the vectorness of it's just going to become positive and negative signs to indicate the positive direction and the negative direction, and the rest is just scalars. So writing Newton's second law, I would say negative b times v minus k times x is equal to m d2x over d2 squared. And this is Newton's second law, but it's also called the equation of motion. Okay, so the differential equation is the equation of motion. Newton's second law is the equation of motion. Now I'm going to put this in terms of derivatives, and I'm going to simplify it into the format that we were used to from the simple harmonic oscillator. So I'm going to say m x double dot instead of m d2x over dt squared. I'm going to pull the negative b times v to the other side, and that's going to make it positive b. And instead of v, I'm going to write x dot. And I'm going to bring the kx to the other side as well, and that'll be plus kx. And then all that's equal to 0. This is, again, a second order linear homogeneous ordinary differential equation. A second order linear homogeneous ordinary differential, oops, equation. So second order just means the highest derivative that we see in the differential equation is 2, the second derivative. The linear means that if you find a solution x1 and another solution x2 and another solution x3 for any number of those solutions, then you can take any linear combination of those solutions. For instance, uh, a1 times x1 plus a2 times x2 plus a3 times x3 plus dot 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 for all of the functions that you found that solve the differential equation. You could take that linear combination and it too will solve that differential equation. It's ordinary because these derivatives are not partial derivatives, and it's homogeneous because on the other side is 0. If instead we had some function on the right-hand side that couldn't be brought back as coefficients of x or x dot or x double dot, then we would have a non-homogeneous differential equation because of the term that could go on the other side. So with that in mind, I've already discussed with you how they do it in the differential equations class, and that's certainly a useful way of doing it. And I'm going to do it this way because it's the way that it's easiest to see exactly what's happening. So one more step I got to take for this damped harmonic oscillator equation. I should also write that this is called the damped harmonic oscillator equation. I'll write that after I rewrite the equation. And to rewrite the equation, I'm just going to divide everything by m. That's going to give me x double dot plus b over m x dot plus k over m x is equal to 0. This is called the damped harmonic oscillator equation. So this is the damped harmonic oscillator equation. And anytime you see a form like this, these solutions that I'm going to show you 3 of them, these solutions will be the solutions no matter how the differential equation came into existence. Specifically, it's a second order derivative plus some kind of constant times the first order derivative plus some kind of constant times the 0th order derivative, i.e. the function itself, is equal to 0. That is the damped harmonic oscillator equation. And whenever you see that form, you know that the solutions I'm giving you here are exactly the right solutions for it. So one thing you sort of need to understand about differential equations, and this is sort of related to polynomials, for instance. We know, for instance, a second order polynomial, what we call a quadratic equation, can have up to 2 solutions. It sometimes only has one, sometimes has none, sometimes only has imaginary, that sort of thing. But the main thing is it can have up to 2 solutions. And in fact, it has to have at least 2 solutions, even if some of them are redundant. The other issue is that in differential equations, sort of the same thing applies. A second order differential equation actually has 2 what we call linearly independent solutions. Well, again, linearly independent is beyond the scope of this course. I'll just tell you that if you can take 3 functions, let's say x1, x2, x3, and we claim that all 3 of those are linearly independent, we know because this equation is linear that a linear combination of those is also a solution of the differential equation. So if we had these 3 solutions, x1, x2, and x3, each of which solved a particular differential equation, a linear differential equation, then the constant c1 times x1 plus a constant times c2 times x2 plus a constant c3 times x3 will be a solution as well. And what I mean by those 3 solutions being linearly independent is if you take and set C1 X1 plus C2 X2 plus C3 X3 for any number, I'm just doing 3 as an example here. if you set this combination equal to 0, and the only way you can make it true is by C1 equals C2 equals C3 equals 0, then those functions are linearly independent. Okay. In other words, if you could make this into 0 without C1, C2, and C3 all being 0, then they're not linearly independent. So with the second order differential equation, one, we expect two linearly independent solutions because that will be the way that you can form all solutions of the differential equation. And I will tell you right now that linearly independent equations include, for instance, e to the x and e to the negative x. They're linearly independent. Sine x and cosine x are linearly independent. And for instance, one is in some sense is a function, y equals 1, and y equals 1 plus some constant times x is a linearly independent solution from the 1 solution. And then 1 plus some constant times x plus some constant times x cubed is linearly independent as well. And in fact, you could just say x is linearly independent of x squared, and x squared is linearly independent of x. But you could also say something like x is x squared, and x cubed are all linearly independent functions. You could also say x plus and x to the 2 power and x to the 3rd power and x to the 4th power are all linearly independent as well. So those are some of the things we're going to use. So I'll just say again, with this C1 X1 plus C2 X2 plus C3 X3, those three solutions, X1, X2, and X3, are linearly independent if and only if the C1, C2, and C3 has to be 0 to make this equation C1 X1 plus C2 X2 plus C3 X3 equal to 0. So now I'm going to kill that because we don't really need this for the problem, but I will tell you, I wanted to write down the examples of linear independent functions. So linearly independent functions. So sine x and cosine x are linearly independent. That's one set. Another set is e to the x and e to the negative x. Those are linearly independent. Another set is e to the x, e to the negative x, and e to the 2x. Those are linearly independent. And then in terms of polynomials, I would say that 1 plus x, and I would say x squared and x cubed are linearly independent. There's actually more in the polynomial range as well. And I could just say 1 is linearly independent from x as well, but 1 plus x is good, and you can sort of see what I'm getting at. You could, in fact, call the polynomial a scalar plus another scalar times x to the 1st power plus another scalar times x to the 2nd power plus another scalar times x to the 3rd power, and keep on going forever. So now that we have that, I'm going to go ahead and use the method that I introduced to you in oscillations example 1 to find a solution to this differential equation. And what I'm going to do is I'm going to make a hypothesis. So hypothesize or let's call it a hypothesis instead of saying hypothesize, because that would take a whole completing another sentence. So hypothesis, oops, I just erased a bunch of stuff. Hypothesis is x is equal to a e to the rho t. And again, the reason why we chose this, as I explained in oscillations example 1, is because the first order derivative of this is in fact something times the 0th order derivative of this. So instead of a comma, I'm going to put a implies. So this means that x dot is a times the derivative of e to the rho t, and the derivative of e to the rho t is e to the rho t times the derivative of rho t. So we get rho e to the rho t, and similarly, x double dot is the derivative of that, so that's going to become rho squared. Oops, I left out an a here. Let me fix that real quick. I don't know why I left it out, but this one should have been rho a e to the rho t, and this one's going to be rho squared a e to the rho t power. So we now have the three derivatives in terms of this hypothesis function that we used as the solution. Now I'm going to plug it into the differential equation. First we have x double dot, which is rho squared a e to the rho t, plus b over m times x dot, and x dot we found was rho a e to the rho t. And then the third term is the zeroth order derivative. That coefficient is k over m, and we just plug in x, which is a e to the rho t, and all of that's equal to 0. But you can see that there's a common factor of x of t in all of this, so I can write rho squared plus b over m rho plus k over m, all that in parentheses, times x of t, which is the a rho e, or excuse me, a times e to the rho t. So this equation must be true for at all times. So the only way it can be true is by the parenthetical rho squared plus b over m rho plus k over m is equal to 0. So I'll just remind everybody, must be true for all t values. Therefore, rho squared plus b over m rho plus k over m is equal to 0 is what we call the characteristic equation. That's the characteristic equation. Again, you'll learn about this in differential equations, but right now we're just going to use that. This is just a simple quadratic equation, so all we really have to do is use the quadratic formula, and that's what I'm going to do. Of course, the quadratic formula, if you've ever taken time to memorize completing the square, or at least understanding it, then you can just complete the square on ax squared plus bx plus c equals 0, and you'll get exactly the quadratic formula. That quadratic formula in this case turns into rho equals negative b, which is the negative coefficient of the linear term. So the linear term is rho times b over m. So the coefficient is b over m. So I write negative b over m plus or minus. Now it's the square root of b squared. So this means b over m squared minus 4 times a, which is 1, times c, which is k over m. All of that should be divided by 2 times a, but of course a is again just 1. So that's what actually we get for our solutions. And you can see something that hopefully you learned when you were talking about quadratic equations and high school algebra 1, high school algebra 2, pre-calculus, that sort of thing. Specifically, you have, in the event that the radical is 0, you only have one solution. But in the event that the radical is not 0, then you have a solution corresponding to what's under the radical being negative that involves an I. And if under the radical the quantity is positive, then you have another part of a real solution. So you get two independent solutions, but both of which are real. So that's where the three types of solutions comes from. So let's first off consider, I'm going to rearrange this row in a little neater fashion. I'm going to go ahead and say rho is equal to negative b over 2m, because I just went ahead and took that denominator and put it with the fraction and I have to do it with the other fraction as well, but this is going to be plus or minus. I'm going to take the 2 that I used on the b over 2m. I'm going to take that also and stick it in the denominator inside the square root. So in order to put a 2 inside the square root, it's going to become a 4 inside. So I'm now going to say square root 1 over 4 times b squared over m squared, that's just me squaring the parenthetical expression, minus 4k over m. And this, of course, is negative b over 2m plus or minus the square root of b over 2m whole quantity squared. Notice that becomes b squared over 4m squared, which is exactly what we'd have if we distribute the 1/4 to the first term. Now I'm going to distribute the 1/4 to the second term. You can see that the 1/4 is going to cancel out with the 4, and in this case, we're just going to get minus k over m. So that is our solution, our value of rho that solves it. And as I said, it's a second order differential equation, and the most general solution, since it's second order, should be a linear combination of two linearly independent solutions. That being said, we have to figure out exactly what those solutions are. So we can go ahead and say, let's take b squared, or excuse me, b over 2m quantity squared. So let's say case 1, b squared over 4m squared is greater than k over m. That would mean that the solution is completely real. Meaning it doesn't have an I part. And the problem with that is the I part in an exponential is the part that gives you an actual sine or cosine. If you don't have an I in there, you just get e to the x, and that's just exponential growth or exponential decay, something along those lines. So in this case, what we have to do is say, all right, well, our solution is then x of t is equal to, let's say, a times e to, in this case, we're going to take the negative b over 2m times t. That's just for the negative b over 2m part, but that's going to be plus or minus. But in this case, I'm just going to take the plus symbol of the square root of b over 2m squared minus k over m. That also times t, and that's one of our solutions. Now I add the linear combination of the other solution, which is the same thing, but when I have the minus here. So now I'm going to have be to the negative b over 2m times t. Now this time it's going to be minus the square root of b over 2m squared minus k over m, and this also is times t. So that's the general solution, and this solution is called overdamped. In fact, it's overdamped, and that means it's basically an exponential decay. So I actually took the time to choose some very key values of b, m, and k to fit this category. So for instance, b squared over 4m squared greater than k over m is satisfied with k equals 4, m equals 1/2, and b equals 4. So when you use that, you can actually get a overdamped solution, and here is a graph of that. So if you're looking at these three equations, you'll see that the one I just did was basically, well, essentially it's part of what I have in the black line there. So the black curve, the very bottom graph, is e to the negative b over 2m times e to the positive square root. Even if you added the other square root, you'd still get the same solution, but that's the black curve that we're seeing here. That is the overdamped. So I will label that accordingly. I will actually do it in black so that it matches. This one's overdamped. Now you might guess, and you'd be right, that these others are the other cases. This one, the red one, is called critically damped. And critically damped means b squared over 4m is equal to k over m. Overdamped meant b squared over 4m squared is greater than k over m. And then this purple one here, this is underdamped. And that corresponds to b squared over 4m squared being less than k over m. So you end up getting that critical I in the exponent, and e to the I theta gives you cosine theta plus I sine theta, and therefore you get the real part as having an oscillatory motion, the cosine theta term becoming oscillatory. So that's the end of all of it, but I just wanted to show you right now the overdamped portion, which is what we just worked out. So now we have an equation for overdamped, and that's what it is. Another way we can look at it, though, let's say case one continued. There is that common factor that really is an exponential decay, and that common factor is e to the negative b over 2mt. So we're going to say x is equal to some constant. We can do a constant right here in front of it. That would be acceptable. But the main thing is we have to have two additional two constants above whatever the row became. So I can say a e to the negative b over 2m. I wrote that way too small. Let me fix that a little better. Oops. It's supposed to be erasing. All those times I try to get it to erase. All those times I didn't want it to erase and it erased. Now when I really want it to be erased, it didn't. Okay, so that is taking into account one of the possible coefficients or constants that we need. Remember, a second order differential equation is like integrating twice, and each time you integrate, you generate a integration constant. So you obviously, if you have a second order differential equation, you should have two integration constants that you got to deal with, and that's what we're showing here is one of the constants is a. Now the other one we can say is we'll just leave the a out in front of this, but we're going to say square root b over 2m quantity squared minus k over m times t. Now I'm going to say plus. Now I'll put another constant. This time I'll put it b. In principle, I could have just left the a from being out in front and just put an a in front of the first e and a b in front of the second e. That would be acceptable as well. I just chose to do it this way. This time we get e to the negative square root. It's the exact same square root quantity, so I don't feel obliged to write it again. I'm just going to put it like that and put the t after it. But that's the complete solution for overdamped. Or the overdamped case. Okay. Now that was again overdamped was specifically b squared over 4m squared is greater than K over M. And like I said, quantities that I use for this could have been, for instance, K is equal to 4, M is equal to 0.500, and B, in this case, would be 4 as well. So let's double check on that. That's B squared. That would be 16 over 4M squared. So B squared would be 16 over 4. That gives me 4. And then divided by 1/2 squared. That gives me 4 in the numerator times the 4 I already have. So that's like 16. And then K over M is just 8. So clearly that fits the criteria. And I don't like this unsymmetric parenthesis. I also don't like that red marker being there. That's not helpful at all. So this is my 4 down here, and this is the parenthesis that I'm trying to use. So that was our first case. Now we're going to consider case 2. Case 2 is going to correspond to B over, all right, let's do it, B squared over 4M squared is equal to K over M. This one is called critically damped. Now, for this case, rho, which was equal to negative B over 2M plus or minus the square root of B over 2M quantity squared minus K over M, that was rho, but this part's going to be 0. Therefore, we only have one solution. I don't want to write that in there. I'm going to write it below. Only have one solution. So since we only have one solution and we really want, since it's a second order differential equation, we want to have two linearly independent solutions. Well, we can multiply one of these functions by 1, and it'll still be this function e, basically, by 1. And then we can also take that e and multiply it by t, t being a first order polynomial. So that would give us two linearly independent solutions, even though I didn't stress that as linearly independent, it is. So I should probably go back and write that. But now what that means is our solution is x of t is actually equal to a times e to the negative b over 2mt. And then I'm just going to multiply that by 1 plus b times t. That makes two linearly independent solutions, one of which is e to the negative x, and the other one is t times e to the negative x. And you can, of course, go ahead and try plugging this back in. I highly, highly, highly recommend you do that to see that it does. It is kind of messy. You've got to use the product rule and all that stuff and taking their derivatives, but that actually is the solution. And this one's called critically damped, and it's the red curve, if I remember correctly, on the graphs that I showed you. So if I turn back to the graphs in the equation, the critically damped is that red curve right there, which of course corresponds to this equation. Notice I just arbitrarily chose the constant in front of the e and the constant in front of the plus sign to be 1, and then what we called b in that previous solution I called 4, and that works just fine. So that's what the critically damped looks like. We've now covered the critically damped and the overdamped. Now I have to do the case 3, which hopefully you've already guessed what that's going to be. So now for case 3, this is when b squared over 4m squared is actually going to be less than k over m. That means rho equals negative b over 2m plus or minus I times the square root. Now, since b squared over 4m squared minus k over m gave us a negative under the square root, which produced that I'm going to write it in the opposite order and it'll automatically make it real. So in this case, I have to write k over m minus b squared over 4m squared as my rho value. And now I have, again, two linearly independent solutions, e to the it and e to the negative I times t. Again, there's a coefficient between the I and the t. It's that square root thing, which, by the way, we call omega prime. So I'm going to define this quantity as omega prime. So when we write this out, what we're going to have is x of t is equal to, and you can put this a out in front. That's what I'm going to do. Or you could group it with the other parts. What we're going to do is say a times e to the negative b over 2mt times e. Well, actually, let me keep it this way because there's a step I'm skipping, and I'm afraid that might be bothersome to you. So I'm going to try not to do that. So I'll put plus I, the square root of k over, well, actually, y'all have expressed exactly, you have it shown exactly what this omega prime is. So I'm going to go ahead and say omega prime t plus some other constant, let's call this one b, times e to the negative b over 2mt minus I omega prime t. So that's one way we can write it. But remember that when you raise a base to a power that has a sum in it, you can get that same quantity by separating the sum and making it two bases multiplied by each other. So in other words, I can split this e to the negative bm b over 2mt from the e to the I omega prime t as follows. I'm going to choose to do it as a e to the negative b over 2mt times, now I'm going to say e to the I omega prime t plus b e to the negative I omega prime t. And that is the actual solution. Uh, if I had chosen to, instead of putting the a out in front of the e to the negative b over 2m, if I had done it like this and said e to the negative b over 2m times t, and then had a e to the I omega prime t plus b e to the negative I omega prime t, then you can see how this result in the parentheses can make a cosine term and a sine term. So ultimately, what your author calls it is x of t is equal to a e to the negative b over 2m times t. That's you can think of that as like a exponential decaying envelope that basically causes the cosine function to exponentially decay. That's what we're shooting at here. So we can go ahead and write it with a cosine in front of it, and this would be cosine omega prime t. And your author doesn't do this, but I generally like it because right now we're looking at not having uh, two constants of integration. So I generally put this as omega prime t plus phi. So that's the more general, nicer way of writing the solution. So what I'm going to do is say this is the solution for underdamped. And remember, the underdamped case meant that b squared over 4m squared was actually less than k over m. Similarly, we found that this solution right here is for critically damped, which we realize corresponds to b squared over 4m squared is equal to k over m. And then we also have the solution for case one, which is overdamped, and that is this solution right here. And that's for the overdamped, which corresponds to, of course, b squared over 4m squared being greater than k over m. And that's it. That's the three solutions for this damped harmonic oscillator. And this is their three graphs that I borrowed from Desmos, just throwing them in there. Notice I didn't take the time to show the second e to the negative square root, but you could put that in and tweak it, and you're going to get basically the same black curve. Notice the purple curve is almost like it's in an envelope for its amplitude, and that envelope is an exponential decay. To show you that, I think it might be nice if I put it in a slightly different color. So what we can say is there is an exponential decay curve that goes on like this, and of course it's both upwards and downward. So in this case, it comes like this, and you can see that this purple curve, or shoot, yeah, this purple curve goes back, crosses over again, crosses back again, so on and so forth. And that's what they mean by underdamp. As you can possibly imagine in terms of a physical solution, if you've ever went in a restaurant that had a door that swung both ways to the kitchen, that's often the case for the waiters and waitresses to come in and out. You would often see that door when the person comes through, opens all the way up. They keep walking through, it swings closed, goes past closed, comes back uh, into the dining area, and then back again like this a couple times. That's underdamped. That's exactly what an underdamped case is. If you've ever seen one where it just swings really quickly and comes to a stop, that's overdamped, and critically damped is sort of somewhere in between. So I hope that helps. That ends this session. So have a good day.